Hi, my name's Gareth McDowell from 493K, and I'm going to spend 5 minutes give you an overview of what we do at 493K. So we supply temperature, thickness, pressure, and training solutions for rotomolders. For any of you who are wondering what 493K means, that is a temperature in Kelvin equivalent to 220 Celsius, which is the maximum optimum temperature of the inside air that you should be cooking your polyethylene part to in rotational molding. So what do our products do? They measure temperature, pressure, and thickness of your parts to optimize your process cycle times, to help you troubleshoot your scrap problems, identify machine faults and inefficiencies, improve process controls and efficiencies, and adjust for changes in ambient temperatures. We have 4 models of the K-Pack, which is the temperature and pressure monitoring equipment. K for Kelvin, temperature, PA for pascals, pressure, and AQ for acquisition, so temperature and pressure acquisition. Our standard unit, featured here on the left of the screen, will run for 5 cycles of 20 minutes oven times before you then need to change the cooling packs inside, which keep the electronics cool. The Junior 3 cycles of 20 minutes. The Mini 2 cycles of 20 minutes. And then for extended oven times, we have the Extreme, and that will run for up to 3 hours before the electronics coolant packs need to be changed out. So that's our K-Pack product. Why do we want to measure temperature in rotational molding? If we measure temperature in rotational molding, we will have a graph that looks not unlike this one in front of you now. On the left-hand side, where the temperature is rising straight up, that is the ambient air temperature. So when it rises to, in this case, 300 degrees Celsius, that is when the mold is going into the oven. Then at the end of that 320 degrees Celsius block, it drops down again to the ambient temperature of the room in and around 30-40 degrees Celsius. So obviously the mold has then come out of the oven and into the cooling bay. The funny shaped graph with the bumps on it, that's the temperature of the air inside the mold. And if you measure that temperature inside the mold and you analyze the graph, you will be able to determine that there are 7 different stages to rotomolding: the powder heating, the wall building, the consolidation of the material, the melt cooling, then the solidification, then the releasing of the part from the tool wall, and then the post-release cooling. So 7 stages of rotomolding. Actually, what's happening is these 7 stages are not discrete, but they are often simultaneously running together. And you can see that in the yellow blocks, I've highlighted what is happening during those periods of time. What's very interesting is that the thickness of your part is only being dialed in. It's only being determined over a very small amount of the oven cycle. And so therefore the rotation speeds and rotation ratios are especially important at that wall building stage, which happens in and around the 1 and 2 areas as shown in the graph. The other product that we have developed here at 493K to enable the molder to easily measure the thickness of their parts accurately is this K-Matron thickness measurement product. It allows you to measure wall thickness from 0.1 mil up to 30 mil. It can be used for all non-ferrous materials, so any plastic materials, even cast aluminium molds, it'll allow you to measure the thickness of those. This K-Matron is linked to a receiving unit, and that receiving unit will receive the transmitted thickness data from the K-Matron, allowing you to record it on the shop floor. Why does thickness feature so highly in the control and improvement of rotationally molded parts. If we look at simple beam theory within mechanical engineering, we find that the deflection of the beam is inversely proportional to the cube of the thickness. That means if the thickness goes up a little bit, then the deflection comes down a lot. Or conversely, if the thickness goes down a little bit, the deflection goes up a lot. This is based on classic beam theory regarding the stiffness and the mechanical properties of the material that is under test. So as an example, if the thickness of your rotomolded part, if you were to cut your part into thin beams and support them at either ends of that beam and put a force on the top, this simple beam theory would say that if your thickness increases by 20%, then your deflection will be 0.6 of what it would be for the original thickness. And if your thickness falls by 20%, your deflection is twice that of what it would have been. So thickness is very important when it comes to determining the structural integrity of your part. There's no point carrying out all the FEA on your parts before they're designed, only to find that when you're in the process of making these parts, a variation of plus and minus 20% can completely throw it outside the acceptable limits. So what variables control the wall thickness of your part? We divide these into two sections: local mold temperature, so the temperature of the local part of that mold, and the powder pool residence time, so how long is the mold in the powder pool at the bottom of the mold when it's rotating. So those two factors will determine how thick the part will be at that point. And here are some examples and observations of how the process and the different parts of the production parameters will affect the thickness of your part. So we'll not go through each one of those individually, but you can pause the video and read those at your leisure. The other product that we have developed is what we call the Rotorocket, which is a uniaxial benchtop rotational molding test machine. It comes with a glass mold as well as steel molds and allows you to observe powder flow. It allows you to measure the temperatures as you're cooking a rotomolded part, checking for the powder layup and the quality of that powder. It allows you to observe foam as it blows. It allows you to perform molded part tests. So just like we talked about earlier, stiffness tests could be carried out on the parts. It allows you to observe the release process, so you can see through the glass mold as the part releases from the surface. You can check different rotation speeds, and you can also view the melt through a microscope through the glass mold. It also is a great little tool for checking your graphics, your labels. And then finally, the K-label is a very simple little product that we supply where you can attach it to the vent pipe, and there will be thermochromatic changes to the label depending on what temperature it has reached. So basically, the higher the temperature that your part has reached in the oven inside air, the more grey blocks there will be on this label. So it gives you a recorded value of the peak internal air temperature that the label has reached. So thank you very much for your time. If you have any questions or you want prices for any of the products that I've mentioned there, please just drop me an email, gareth.mcdowell@493K or to sales@493K.com. Thank you very much for your time.